All right, on homework 4.4b, we're dealing with Riemann sums, and I'm going to actually help with a bunch of the things that aren't necessarily Riemann sums. Here we've got a comparison of velocity versus time, and I'm going to highlight, this is about a car traveling down a straight road, and I'm going to highlight the key things that I see when I'm just like looking at this really quickly. During what intervals of time is the acceleration of the car positive? This is the velocity, not the acceleration. What you need to know here is that the acceleration is the derivative of velocity. So this is asking where is the derivative of the velocity positive. This means the slope of v of t is greater than 0. Where is the slope positive, or v of t is increasing? It's basically asking us on what intervals is v of t increasing. And we can see that v of t is increasing from 0 to 35. And it also increases from 45 to 50. So this interval union this interval is the areas where the velocity is increasing. And since velocity is increasing, v prime is greater than 0. The derivative of velocity is the acceleration, which is what it was asking us about. All right, another acceleration question. This time it asks for the average acceleration. Average acceleration means, on average, how much was the velocity changing by. This is just the slope of the velocity. This is the average of the derivative. And so we want to know how much did the velocity change by between 0 and 50. So this is just v of 50 minus v of 0 divided by 50 minus 0. How much did the velocity change by from beginning to end? And we can find this in our table. The velocity at the end was 72. The velocity at the beginning was 0. And so the velocity changed by 72 feet per second over the course of 50 seconds. And so this is, I guess we can simplify this. This is 36 25ths feet per second squared. The way we get these units is because the velocity was changing. This is 72 feet per second. That's how much the velocity changed by, 72 feet per second in 50 seconds. So feet per second, we write as feet per second squared. One more acceleration question. The acceleration of the car at t equals 40. So this is, the acceleration is the derivative of velocity at t equals 40. So it wants, what is v prime of 40 about? And there isn't a way to get exactly what v prime of 40 is because we don't have a function, we can't take a derivative, but we can make an approximation. And the way we do that is we look at 40 and we want to see what the derivative is. We don't have a function to take a derivative of, but we have a few different approximations that we can use. We just need to find a nearby point and find the slope between those 2 points. So we could use this point and this point. We could also use this point and this point. That's an appropriate approximation. Or you can actually use the 2 points surrounding it, and that's another approximation of the slope, v prime of 40. So there's 3 different approximations depending on which points you choose, and it doesn't matter which one you do choose. The last one I'm going to do here is finding the midpoint sum for the data by using the midpoints of 5 subintervals. So again, I'll do this in blue so we don't get confused. The midpoint sum, the way it works is we skip the first data point and we use the second. And the reason it's the midpoint is because we go both to the right and to the left until we reach another point and we make a rectangle. And that data point will be the midpoint of our rectangle. This data point at t equals 5 had a height of 12. We skip this one and we go to the next one. We're going to go both left and right. This is the midpoint of a rectangle. At t equals 15, the height was 30. Always go off of the table, not off of the graph. You can't get exact values off of the graph very easily, whereas all the exact values are in the table. We're going to skip this data point and go to here. And our midpoint of our rectangle is going to be here. This is a height of 70. We're going to skip this one, make our rectangle, at t equals 35, the height was 81. And our final midpoint is right here. The calculations we're going to do is we need to show that we're adding up the area of each of these rectangles. And so we've got the base times height for each rectangle. I'm going to do that below. The base of the first rectangle is 10 times 12. I guess I should label things. This is the integral from 0 to 50 of v of t dt is approximately equal to, this is an estimate, it's not exactly equal to, it's approximately equal to 10 times 12 plus 10 for the second rectangle times 30 plus 10 times 70 plus 10 times 81, and the last one was plus 10 times 60. So I don't have a calculator with me, but you would type this in a calculator and see what it equals. The answers are on the back, you can check there. Any ones on the back I want to do? Yeah, I'll do real quickly. You've got another table here, and it asks you to find a midpoint Riemann sum again. So make sure you do a midpoint Riemann sum on this one. In B, this is the one I want to go over here. It says, based on the values in the table, what is the smallest number of instances which the acceleration could be 0? Notice that it gives you the velocity. It's asking you about acceleration. So you need to use your knowledge that acceleration is the derivative of the velocity. So this is the same as asking, what is the smallest number of instances the derivative of velocity is equal to 0? And this isn't about Riemann sums. This is one of our theorems. To see where the derivative is 0, you should use Rolle's theorem. And Rolle's theorem says if you have a function that is continuous, differentiable, which we have here, if the function is differentiable, it's also continuous, and the y value at the beginning and the end are the same, then the derivative must be 0 somewhere in between. And I want to draw your attention to this. When t is 0, the velocity is 7. When t is 15, the velocity is 7. And so the derivative must have been 0 somewhere between here. Later, when t is 25, the velocity is 2.4. When t is 30, the velocity is 2.4. And so again, there must be a 0 velocity somewhere between here. There may have been a 0 derivative somewhere in between here. There may have been another place where the acceleration is 0, but we're guaranteed at least 2. The way our justification sentence should go should be, there are at least 2 instances on the interval from 0 to 40 where acceleration equals 0 because the function, because instead of saying the function, we should say v of t is differentiable and by Rolle's theorem, since v of 0 equals v of 15 and v of 25 equals v of 30, v prime of c equals 0 for some c on, I would say, on the interval 0, 15 and on 25, 30. So basically, there are 2 different places where the derivative needs to be 0 because by Rolle's theorem, you had the y values the same in 2 different places. You also could have used the mean value theorem on this as well. You had multiple options here, but you needed to use either Rolle's theorem or the mean value theorem. Hopefully that's helpful and you do well.